number that you rolled your first turn?
You roll the 2 dice at the same time.
Why?
Because that's a different problem.
How do you just assume that you do that? It doesn't matter if you roll at the same time. It's still the same chance. You know
The second die is not dependent on the first die. What you roll on your second die does not depend on what the first die rolled. Whether you roll them at the same time or independently of each other. But I do, okay, fair enough. I do like the thought, though.
I mean,
I'll consider it. It's in my brain.
We did the same thing.
Yeah, we did the same thing.
Like, that doesn't make sense to me. 32 rolls and you're not going to get points on, like, that's a ton of rolls. I feel like you could be able to 5 out of 6 chance of not.
Well, maybe if we finish in time today, I can go down to the workroom and get some dice and we can test it out.
We can all play number cubes.
We can play number cubes.
Like, why would the probability change based on the order that you roll?
The probability doesn't change
So
because the rolls are independent of each other. What you roll in the first roll does not affect.
Well, no, but I think what he meant was like the
does
separate
that not make an
cubes.
argument, though? Like, is that
Okay,
not
separate cubes, but they're independent of each other. The second cube is not dependent on what happens with the first one at all.
Yeah, but theoretically you can get whatever number on the first cube, but on the second cube, there's like a 1 in 6 chance that it'll match it.
I know what you mean. What are your colors?
What's the cause of the museum?
I had a learning task the other day and I just had to move the chairs back.
I like it like this.
Like,
We
I
always
made
turn
my
around and
probability
talk about it.
on the fact
Uh-huh.
that on
Now you don't have to.
the assumption that you roll
Okay.
points.
Fair enough.
We can stare each other down.
Okay, so those of you listening to the recording of this, there was some discussion about life on the expected value part of the homework. And Miss Willoughby is considering their thought process and trying to explain my thought process. But there's the answer to number 5. And you can check, I'll post my notes on my website and it'll be there also. Okay, so let me get rid of the notes from the previous class and then we'll, okay, good enough. All right, today we're going to revisit, for those of you that had Accelerated Math 1 at the high school, we are revisiting binomial distributions. For those of you that did not have Accelerated Math 1 at the high school, you may not have seen this. So what I'm doing is teaching it as though no one has ever heard it. Okay? So, first thing we want to talk about are binomial distributions. What does the bi in the binomial tell us that's probably going to happen? It's going to involve something about 2. All right. So what is a binomial experiment? A binomial experiment must satisfy the following conditions. And do you see what condition 2 is? There are only 2 possible outcomes, success or failure. So that's why we call it a binomial distribution. We have 2 possible outcomes. So number 1, the experiment must be repeated for a fixed number of trials, where each is independent of the other trials. So the outcome of one trial will not affect the outcome of the next. Does that make sense?
Yes.
Okay. There are only 2 possible outcomes of interest, success or failure. The probability of success is the same, so it's not going to change. And the random variable x counts the number of successful trials. So in our examples, we're to describe whether the experiment is a binomial experiment. And if it is, specify the values for n, p, and q. And if it's not, explain why. Example 1, a certain surgical procedure has an 85% chance of success. A doctor performs the procedure on 8 patients. The random variable x represents the number of successful surgeries. Okay, is there a fixed number of trials?
Yeah.
Yes. So what is n? 8. Okay. Are there only 2 possible outcomes or failure?
Yes.
Yes. So we check, check. 3, is the probability of success the same for each trial? Yes, and what is that probability of success? Okay, so P equals 85.85. And does the random variable X count the number of successful trials? Yes. So, is it a binomial experiment? Yes. Yes, it is. We checked off all 4 things. So now we've got said to tell us what N, P, and Q are. So N represents the number of trials. We have 8 patients. We have 8 trials. P represents the probability of success. And Q would represent the probability of failure. The probability of success is 85%. What does that leave for failure? 15%.
That's a pretty good surgery chance.
You think?
No.
I would want mine to be even higher.
Well, but I mean, like, consider if it's like some like 30.
That's true.
Yeah, we only.
If it was 85% and it was elective, I still don't know that I would do it.
I'd do it.
For elective?
It means it won't work. You'll probably have to do it again.
Are we talking like failure, death, or are we talking like failure?
No,
You're like Michael Jackson.
okay, death would represent failure, yes. But it doesn't have to be that extreme.
Like it could be like a long.
Like if I had an issue, I would want it fixed if it was a real person.
Like if you had a problem with your back and you had back surgery, and after surgery your back still hurt, I would not consider that a success. But that doesn't mean you're necessarily dead.
Yeah.
Okay.
I'd still do it. If I needed a surgery and there's an 85% chance I would do it.
As long as it wasn't elective. As long as it was something that was 100% necessary.
Yeah.
All right, number 2. A jar contains 5 red, 9 blue, and 6 green marbles. You randomly select 3 marbles from the jar without replacement. The random variable X represents the number of red marbles. Okay, so the random variable X represents the number of red marbles, so it's either a red marble or it's not. Are we good with that? Okay. Is there a fixed number of trials?
Yes,
3.
Yeah.
Okay. Is the probability of success the same for each trial?
No.
No. What wording in here tells us that it fails step 3? Without replacement. So that's going to change the probability of success. So this is a no because the probability of success does not stay the same for each trial.
Did you hear about those new goggles they invented that can detect stroke with 100% accuracy?
No, but that's awesome.
Yeah.
Like what?
No, like if you're in a hospital, you put them on, and if your like eyes start moving, like and you're gonna have one, it tells like you if you're gonna have a stroke over just vertigo.
So if you want to tell anyone to get stroke, you just have to be having those on you all the time. I feel like that. You do it.
No.
Or if you had them in the hospital and somebody came
yeah,
in
like with dizziness,
that
like
felt they might, yeah.
MRIs can only do it with an 85% accuracy.
Or
And
you
they
just
cost
always wear them.
That's awesome. That's awesome.
Do they make them zebra print?
Okay.
they look like 3D goggles.
Any questions about determining whether we have a binomial experiment going on? Okay. Now let's look at, once we've determined if it is binomial, what can we do with it? So what we're going to do is find the binomial probabilities. We looked at this last year. Not all of you may have, so let's go through it slowly. The probability, and there's 2 ways we can do this, is the combinations of n choose x, where x represent our number of successes. P to the x, q to the n minus x. Now, combinations, do y'all remember the formula for combinations? More than likely not, I don't imagine.
It's like C.
So it's combinations are n factorial over, we used r. Do y'all remember r, n minus r? R factorial times n minus r factorial. Maybe not. But here, x represents what would have represented r for us. Okay, times p to the x, q to the n minus x. And then I'm going to talk about a shortcut on our calculator after we have done this a little bit. You have to be able to explain to me the math that's happening in order to be able to use the calculator. So we're going to do a couple that we kind of show our work. So a survey indicates that 41% of American women consider reading as their favorite leisure time. I am not in that group. If 5 women are surveyed, find the probability that exactly 2 of them respond yes to to that being their favorite leisure activity.
Do you like leisure reading maybe?
I like to do activities with my family, like going for a hike or going for a bike ride
Going skiing.
or playing with the dog in the backyard.
Alright, so 1, that's no.
So I'm a no. I'm not a reader.
Laura?
Unless everybody's in bed. If everybody else is asleep, I'll read.
Laura? What do you
I like reading, but it's not my favorite
No.
thing to do in the world.
I like
Yeah.
to read.
Do you like leisure reading?
I prefer writing.
What did you just say?
Do you like leisure reading?
I do.
Alright, she does. Do you? Go ahead.
Did we get up to 41%
Alright, so
in
that's
here?
3 no's and 2 yeses. So we're about right there.
We're right on it. All right. So, exactly 2 of them respond yes. What is the probability that occurs? So, first of all, is this a binomial experiment? Are there 2 outcomes?
Yes.
Yes, I either like reading or reading's not my favorite. Do I have a fixed number of trials? Yes. Does the probability remain the same? Yes. Okay, so I'm good. So I'm going to do the combinations of, how many trials do I have? 5. And how many successes do I want?
2.
2. Combinations of 5, choose 2. Of, what is the probability of success? Good, 41%, 0.41. And we want 2 successes. So how many failures would that give us?
3.
3. And how do I get the failure? 1 minus the success.
Is that it?
Okay, so let's revisit how to use our calculators to do this.
345242009.
You are correct. So it's 5, and then you go over to math, and you arrow over to probability, and combinations is choice 3. 5, choose 2, of 0.41 to the second, and 0.59 to the third. Are we good? Let's do 3.
How do you choose what power to use? Is it based on like the group size? Do you just kind of round that?
You choose, this says exactly 2 of them respond. So the successes would be 2.
Alright.
And this gave us approximately 34.5% or 0.345. There's our probability. Okay, now part 2 of this question is worded differently. At least 2 of them respond yes. So at least would be the probability of 2 or 3 or 4 or 5. Well, when we do probability and it's or, what do we do with those individual probabilities? Add them up. Okay? We've already found 2. So if that group over there would find the probability of 3, gentlemen in the corner, ladies right here in the middle, find the probability of 4, and gentlemen back there, find 5. We'll catch y'all next time. Actually, you guys do 1. And I'll tell you why in just a minute. And can you do the probability of 0 for me? Okay. I've already got 2. Point 24 what? 0.23999. So is 0.24 good? Is that good for y'all, fellas?
That'll work.
That'll work. Okay, ladies here, what'd you get?
496.
Point.
496.
You did?
Yes. I don't know. Is that not right? Okay. What'd you get?
I forgot forgot to switch the thing.
Oh wait, I know I did wrong.
Oh, okay, good.
Yeah, it's like
Hey.
I'm sorry. It's .083.
Good.
Yeah, that was really wrong.
No, you're good.
Hey.
All right, gentlemen.
0.012.
0.012. Okay, so this is approximately 0.68. Make sense? Okay, versus part 3 says fewer than 2 of them responded yes. So fewer than 2 would be the probability of 0 or 1, right? Okay. Yeah. Tell me what you get for 0.
Yeah, there's
0.0.
715.
Okay. All right, ladies, what y'all get for 1? Good. Now, what do you notice about the probability of 2, 3, 4, or 5
They add
and the probability of 0 and 1? They add up to what?
up 1.
Why? Why do they add up to 100%?
Because they're 100%.
Because it's everything. Yeah, together it's everything. So, on this one, if I didn't want to find all 1, 2, 3, 4 of them, is it fair to say that I could have done 1 minus the probability of 0 or 1, the complement of that?
Yeah.
I was wondering
Yes.
how we do it.
And we certainly could have. We could have done it that way and gotten the exact same result. Do you see that? Okay. All right, number 2. Oh, too far. There we go. 75% of American households subscribe to cable TV. You randomly select 6 households and ask each if they subscribe to cable television. Construct the probability distribution. So we need the probability that 0, the probability that 1, the probability that 2, the probability that 3, the probability that 4, the probability that 5, and the probability that 6. That would be my probability distribution. To show the distribution, I have to show every single possibility.
And this is also combinations, right?
This is also combinations. Let's make sure though, 75% you either subscribe or you don't. Whether I subscribe does not affect you subscribe. Yep, I'm good. It's a binomial experiment. So, the first one would be the combinations of 6 choose 0, of 0.75 to the 0, and 0.25 to the 6th. Does that make sense? And then we'd work our way down. All right. So let's work our way around the room again. You guys do 0. You do 1. You guys do 2. You do 3. You do 4. I got 5 and 6.
Would you like to know ours? For number 1.
Oh, you guys are number 1.
.004.
All right, fellas, y'all's was tiny, wasn't it? What'd you get? How many zeros before there was even a number?
3.
3. Okay, and then what was that number?
2, 4, 4, 1.
All right, that's good enough. Okay, probability group 2.
0.033.
Okay, probability group 3. Probability group 4. I'm probability group 5, point this, and I'm 6, and I got this. Now, if I added these up, they would be really close to 100%. Is it going to be exact? No, because I rounded a lot. But it's going to be really close to 100%. Now, let me show you the cheating, but the aid of technology way. You know how to enter this on the calculator. The calculator also has different distributions. One of the distributions it has is a binomial probability distribution. That's what we're doing. So let's go into distributions. Second VAERS. Let's go. Second VAERS is your distributions. You're going to arrow down until you get to binomial PDF. PDF. All right? And, okay, so we had how many trials? We start off with the number of trials. So you do 6, comma. What was the probability of success? 0.75. Now, if we just wanted to know the success of 3 trials, right here I would put comma. I'll show you. You don't do it, just watch me. Comma 3, enter, and did it spit out the same thing we got? Yes, that's exactly what we got by hand a minute ago.
Those trials, probability would be like...
This is the probability of 3 out of 6 being successful. Now, what if we wanted the whole list? How would I do the whole list? So we do second VAERS, go down to binomial PDF. If I go too fast, it scrolls forever, so I have to go slow. There we go. Nope, see, still went too far. Okay. Now, what I want to do is I want the whole list this time. So 6, comma, 0.75. If I just hit enter now, it gives me the list on this screen, which is a little hard to read. So I'm going to tell it, I don't want it right here. I want you to store it. You see the store button? It's called stow. Store it, and let's put it in the list so I can see it real pretty. Second one says to store it in L1. Now, those of you that have an updated operating system, it prompts you for this. You don't have to do all this comma mess. If you go home and update your operating system, it will prompt you.
How do you do that?
Okay, so now see how it did it for me, but it's hard to read on this screen. But since I told it to store it in L1, if I go into statistics now and look in my L1, guess where all my answers are? Right there.
That's so nice.
I'm not getting it.
Okay, let me take a look. Okay, good, good. Okay, you want... Okay. You don't have to use store button because yours is prompting you for it. And now if we go look in L1. No, it isn't.
Maybe you could clear your first.
Why not? This is another great
I didn't do all those.
No.
Okay, let's just go up here
How you doing, Gene?
and enter it there. Go up there, and then I'm going to do a five.
It doesn't do it. That's clearly it's actually a time bomb now. It'll blow up somewhere in I'm just looking for your
Let me play with yours in a minute. Here, I'll swap you right now. Okay, I'm going to pass out our homework, and I'm going to I make that do what I want it to. But a lot of it's bad.
How many times do you
Our matching happens.
Oh yeah, I have.
not good work? Bad call. That'd be sick.
I did that in school. Okay, let me figure out the new ones. That you got the new one. Let me mail those to you. I'm trying to figure out how to make it work.
I think yours can do it too. Same one.
He's got the weirdest hair.
Really?
It's how big the button
Question.
Put it in the zero.
What? How did it froze?
You know what I mean? Like, put the probability and then put it in the end.
I got it.
Tell me if point A is
Make sure you're on a plain screen first. Okay, then go in.
Turn it off. It might be dead. He doesn't know.
Go to binomial PDF. Mixed trials. Don't choose the X value.
Roger, you do point A.
Okay,
You
so
do point
do store and
Well, can you show us one?
then if you go in there.
A. I think you can remove it.
So can you show us A?
Don't give
One
it
A.
full
Same thing for the rest.
Just because it.
Woo! Four tries. Just sound like a commercial. Little Caesars.
Or maybe that's 5.
Okay, this one that has the large amount of
Oh, really?
Yours is just,
Even John.
I just had to figure it out.
Weird hair. All of them.
So, what we do is you start off on a blank screen, set up, you'll look up distributions, and choose primary. And it just prompts you. So we have 6 people, 75%. And then hit paste, and then tell it to store in L1.
It's really tough.
That's where you would do it.
It's like, it's okay.
Then we go into L1.
Never heard that before.
Hey!
Okay.
Yes.
I mean,
I want to downgrade.
Okay.